What is a dinosaur? The word likely conjures an image of a terrestrial titan, a creature like Tyrannosaurus rex, bipedal, with a massive skull and a long, stiff tail acting as a counterbalance. This was the blueprint for large predatory dinosaurs for over 150 million years. But what if the fossil record presented a creature that shattered that blueprint? An animal with the lineage of a theropod, but the anatomy of something else entirely. Something built for the water. This is the fundamental paradox of Spinosaurus aegyptiacus. Today, we open the case file on an animal that forces us to question the very definition of a dinosaur. Now, let's dissect the evidence and solve the case of this bizarre survivor. The story of Spinosaurus is one of loss and rediscovery. The original partial skeleton was unearthed in Egypt in 1912 by paleontologist Ernst Stromer. It was a tantalizing glimpse of a bizarre predator, but tragically, these fossils were destroyed during a bombing raid on Munich in 1944. For decades, Spinosaurus remained a ghost in the paleontological record, known only from Stromer's drawings and descriptions. But in the early 21st century, new discoveries from the Kim group of Morocco began to resurrect the animal, and the creature that emerged was stranger than anyone had imagined. Let's begin by establishing our baseline. Here is a simplified 2D diagram of a typical large theropod, such as Allosaurus. Note the key features: long, powerful hind limbs for efficient bipedal locomotion, shorter forelimbs, and a rigid, muscular tail held horizontally to balance the body's weight over the hips. This is a design perfected for life on land. Now, let's overlay the known skeletal material of Spinosaurus. The contradictions are immediate and profound. Its skull is not the deep, bone-crushing apparatus of a T-Rex, but long, slender, and filled with conical teeth that interlock. This is a jaw built not for crushing, but for snagging slippery prey, functionally convergent with that of a modern gharial. Furthermore, the tip of its snout is riddled with foramina, small pits that, in life, would have housed a network of nerves and blood vessels. When we look at a cross-section of a modern crocodile's snout, we see a nearly identical system of neurovascular canals, which they use as pressure sensors to detect prey moving in murky water. The inconsistencies continue down the skeleton. The hind limbs are surprisingly short and robust for an animal estimated to be longer than a T-Rex. These are not the limbs of a swift terrestrial runner. Analysis of the bone microstructure reveals another powerful aquatic clue. Let's look at this cross-section of a Spinosaurus rib. The bone is extremely dense, a condition called pachyostosis. This is not the lightweight, hollow bone structure of most theropods. Instead, it is found in animals like manatees and penguins, who use heavy bones as ballast for controlling buoyancy in water. And then there is the tail. For decades, it was assumed Spinosaurus had a standard theropod tail. A landmark 2020 discovery changed everything. The new fossils revealed a tail unlike any other known dinosaur, a series of extremely elongated neural spines creating a deep, flexible, fin-like structure. When we place this wireframe model next to that of a T-Rex tail, the difference is absolute. One is a stiff counterbalance, the other is a powerful, paddle-like propeller. This is our paradox. We have an animal classified as a theropod dinosaur, yet its anatomy screams aquatic specialist. A crocodile's snout, a penguin's bones, and a newt's tail, all attached to the body of a giant predator. Was this simply a dinosaur that waded in the shallows? Or was it something far more radical? A fully fledged river monster? To find out, we must go deeper. We must investigate how this bizarre collection of parts could have possibly worked together as a living machine. To solve the paradox of Spinosaurus, we must move beyond simply listing its strange features. We need to assemble them into a functional whole to reverse engineer the biomechanics of this Cretaceous enigma. Our investigation begins at the business end of the animal, the sophisticated sensory and hunting toolkit of the skull. When we analyze a 3D model of the skull, we are looking at a masterclass in aquatic adaptation. The long, narrow rostrum is not just superficially crocodilian, it is biomechanically optimized for movement through a dense medium. A deep, massive skull like that of Tyrannosaurus would create immense drag, but this design slices through water with minimal resistance. The conical teeth, as we noted, are perfect for piercing and holding struggling fish. If we place a diagram of the Spinosaurus jaw next to that of a modern gharial, a fish-eating crocodilian, the functional similarity is striking. Both employ a dental trap of interlocking needles. But the most compelling feature is the sensory web embedded in the snout. Let's isolate the rostrum and highlight the foramina. These openings connect to a complex internal canal system. By mapping these canals, we can reconstruct the path of the trigeminal nerve. This creates a diagram of what was essentially a biological pressure sensor array. Any disturbance in the water, the flick of a fish's tail, the movement of prey hiding in the silt, would register as a minute pressure change on the snout, allowing Spinosaurus to hunt effectively even in zero visibility conditions. Adding to this, the bony nostrils are retracted high up on the skull, far back from the tip. This is a classic adaptation seen in many semi-aquatic animals. It allows the creature to breathe with only the very top of its head breaking the surface, keeping its deadly jaws submerged and ready. Next, we move to the chassis of this machine, the torso and its enigmatic sail. The dense pachyostotic bones are our strongest clue for its lifestyle. Let's illustrate this with a simple buoyancy diagram. An animal with light, hollow bones, like most theropods, would be exceptionally buoyant, bobbing on the surface like a cork. To submerge, it would have to actively fight this buoyancy, expending significant energy. In contrast, the dense bones of Spinosaurus act as integrated ballast. This would have allowed it to achieve neutral buoyancy, hanging suspended in the water column with little effort, much like a modern submarine. This is not an adaptation for wading. It is an adaptation for submergence. This brings us to the sail. Towering over the body, its function has been a subject of intense debate. Was it for thermoregulation? This is now considered unlikely, given the hot climate it inhabited, and the fact that many other large dinosaurs in the same environment lacked such a structure. The more compelling hypotheses are rooted in its semi-aquatic context. One idea is that it was primarily a display structure. Let's visualize this. A 15-meter predator gliding through a river system, its sail slicing through the water's surface. It would be an unmistakable, intimidating signal to rivals and a beacon to potential mates. Alternatively, a biomechanical hypothesis suggests it may have functioned as a hydrodynamic stabilizer. In this wireframe model, we can see how the sail's massive surface area would resist lateral roll, keeping the animal stable while swimming or ambushing prey. The reality may be a combination of both, a display structure that was also co-opted for a biomechanical advantage. Finally, we arrive at the engine room, the propulsion system. The short, stout hind limbs, with their broad, flattened claws, were initially seen as a weakness for a theropod. But viewed through an aquatic lens, they make perfect sense. They were not built for running, but for powerful aquatic locomotion. While we lack fossil evidence of webbing, the flattened shape of the toe bones strongly implies they were connected by skin, forming powerful paddles for propulsion or for punting off the riverbed. But the true engine was the tail. The discovery of its true form in 2020 was a paradigm shift. Let's pull up a direct comparison again. The stiff, tapering tail of Allosaurus versus the deep, flexible tail of Spinosaurus. The latter's elongated neural spines create a massive oar-like surface. Crucially, biomechanical analyses show that the vertebrae have a range of motion that allows for extensive lateral undulation. Researchers tested this directly by creating a robotic flapper modeled on the tail's shape and flexibility. The results were conclusive. When moved in a side-to-side motion, as we can see in this simulation overlaying the muscle groups, the tail generates immense forward thrust. The efficiency of this caudal fin was found to be more than double that of the tails of terrestrial dinosaurs and on par with the propulsive structures of living semi-aquatic reptiles. Assembling these components, a clear picture emerges. We have a predator with a hydrodynamic pressure-sensing snout, a ballasted body for effortless submergence, and a tail purpose-built to generate powerful thrust in water. The evidence from this biomechanical investigation points overwhelmingly in one direction. Spinosaurus was not a land animal dabbling at the water's edge. It was a creature profoundly engineered for an aquatic existence. The question is no longer if it was aquatic, but how aquatic it truly was. This is the heart of the ongoing scientific debate. The biomechanical evidence paints a compelling picture of an aquatic machine. But how did this machine operate in its environment? This is where the investigation moves from anatomy to behavior, and where we encounter the central scientific debate. The data can be interpreted to support two competing models for the life of Spinosaurus. The first is the Shoreline Specialist model. In this reconstruction, Spinosaurus is a semi-aquatic predator, but one still fundamentally anchored to the land. We can visualize it hunting like a colossal heron, wading into the shallows of the vast river systems of Cretaceous North Africa, using its immense size to stand its ground against the current while its sensitive snout detected passing prey. The paddle-like tail could have been used for slow sculling or for a burst of propulsion to lunge at a large fish. Its awkward terrestrial locomotion would have been sufficient for moving between waterways or hauling out onto sandbars to rest and nest. The primary evidence for this model is its lineage. It is, after all, a theropod dinosaur, and a full departure from a terrestrial lifestyle is an extraordinary evolutionary leap. However, this more conservative model is difficult to reconcile with the sheer extremity of the adaptations. If it were merely a wader, why would it need the dense, ballasted bones of a diving animal? Why evolve a tail with the propulsive power of a crocodile's if it only needed to stand in place? The anatomy seems vastly over-engineered for a simple shoreline ambush strategy. This leads us to the second, more radical hypothesis, the aquatic pursuit predator model. This view posits that Spinosaurus was a truly dominant force within the water column, spending the vast majority of its life swimming. In this scenario, it was an active hunter, using its powerful caudal fin to patrol deep river channels, pursuing the giant sawfish and lungfish it shared its ecosystem with. Its time on land would have been minimal and clumsy, perhaps analogous to a modern sea turtle, which only comes ashore to lay eggs. This model elegantly explains every bizarre feature we've analyzed: the submerged hunting sensors, the periscopic nostrils, the buoyancy control, and the powerful aquatic engine, all working in perfect harmony. Isotope analysis of its fossilized teeth further supports this, showing a chemical signature consistent with a diet overwhelmingly dominated by aquatic, not terrestrial prey. The main challenge for this model is terrestrial locomotion. Let's look at this wireframe model showing the animal's likely center of mass. It appears to be positioned far forward, which, combined with the short hind limbs, would make stable bipedal walking extremely difficult, if not impossible. Could it have walked on 4 legs? Perhaps, but its arms and hands don't appear well adapted for weight bearing. How this river monster navigated the land-water interface remains the biggest question mark against this hypothesis. So, what is our verdict? While the debate continues, the scientific consensus has shifted dramatically. The weight of the biomechanical evidence, particularly the discovery of the propulsive tail, makes the simple shoreline specialist model difficult to defend. The aquatic pursuit predator model, while leaving questions about terrestrial movement unanswered, provides a far more cohesive explanation for the full suite of adaptations. The case file suggests Spinosaurus was indeed a river monster, a dinosaur that had taken the theropod blueprint and radically redesigned it to conquer a new aquatic frontier. The precise limits of its domain are what we are still working to define. Spinosaurus forces us to reconsider the boundaries of what a dinosaur could be. It stands as a powerful testament to the relentless creativity of evolution, demonstrating that given the right pressures and opportunities, life can find the most extraordinary solutions. Its bizarre form is not an evolutionary mistake, but a masterwork of specialization, the full details of which we are still uncovering with each new fossil. What is your hypothesis? Do you think Spinosaurus was a shoreline specialist or a true aquatic pursuit predator? Leave your analysis in the comments below. And if you want to own a piece of this investigation, the detailed 3D model of the Spinosaurus caudal propulsor we analyzed is available for our patrons via the link in the description.